Neutrinos. You have probably heard of them. A tiny particle. Why do we make such a big deal of them? What can we learn from them? Neutrinos are elementary particles. They are leptons like electrons, muons and tau, but as opposed to them, they are neutral, which means they are not charged positively or negatively. Neutrinos are actually a group of three different but very similar particles named after their fellow charged leptons, making them the electron, the muon, and the tau neutrino. The only correlation they have with their fellow charged leptons is that when a charged lepton is formed, the antimatter counterpart of the associated neutrino is also formed at the same time. So when an electron is formed, an electron antineutrino is also formed. All those neutrino types, or flavors, are almost massless, but not completely, thus traveling in speeds less than the speed of light, despite some measurements back in 2007 which said that neutrinos travel faster than light, but proved to be wrong in 2012 and were caused by an error in the calculations. But what is really interesting about them is that, as opposed to other particles like photons, they are practically not affected by gravity, and as opposed to other leptons, they are not charged in any way, so they are not affected by electromagnetic forces. They also ignore strong interaction. Because they ignore almost every type of force, they can travel forever in a straight line. So, if we can detect a neutrino, we can know in which direction a high enough energy reaction needed to make a neutrino is happening, and we can observe it and learn about the biggest energy factors in the universe, like black holes, or things that we don't know about yet. So, how do we detect them? Something interesting about them is that they can react with muons, and while they get destroyed, muons get activated and they start moving in high speeds. There, the whole trick happens if this happens underwater. Because, as we all know, light travels slower inside water, so a muon can exceed the speed that light has in water. When this happens with muons, a similar effect like that of planes when exceeding the speed of sound happens, like a photonic boom producing a cone of blue light. So if we have a light detector deep enough underwater that light can't reach it, and then wait for this phenomenon to happen, then we have detected our neutrino. Right now, there are several experiments running around the globe, the biggest being IceCube. In IceCube, hundreds of light detectors are buried thousands of meters deep inside the compressed ice. Most neutrinos, though, still pass unseen, but around 10 times per year the collision happens in the right place and we detect it. So now we leave the era of common telescopes, and it's time to expand our horizons and explore with neutrinos. Thank you very much for watching.